Okay, I guess it's 8 o'clock and we should get started. So welcome back to this final plenary session for PHENO 21. It's a pleasure to introduce our speakers today. Two quick announcements. First, please review the PHENO Code of Conduct if you haven't already. That's available on the Indico page. And also, if you have questions for our panelists, please enter them into the Q&A box, not the chat box, but the Q&A box, so we can make sure that we get to them. So without further ado, our first speaker is Henriette Elvang from the University of Michigan, who will tell us about scattering amplitudes and the double copy Bootstrap.
So thank you very much, and thank you so much for the invitation and the opportunity to present this forthcoming work. So I'll tell you about a new version of double copy that we'll call the double copy Bootstrap. So let me try to put it in context. We know that the landscape of field theory is vast, it's rich, it's interesting, and of course, extremely useful in physics. We have the standard model and beyond the standard model physics that is the focus here of this conference. And then there have been other explorations of the landscape, such as the conformal Bootstrap, where we try to metaphorically characterize the peaks and valleys of this landscape. There are things like the swampland, which asks which effective field theories has UV completions. Then there's the soft bootstrap for exceptional EFTs, such as Goldstone EFTs. And another way that I'll try to argue explores the landscape is using this context of the double copy, asking which theories can be double copied and what can they be double copied to. And that will be the focus of this talk. So a way of exploring the possibilities in field theory from a theoretical point of view using the double copy as a criterion. So what is the double copy? So we should think of the double copy as a map on the space of field theories. I will focus here at tree level, although there are loop versions of this too, but for everything I talk about in this talk, it'll be tree level. So the double copy takes tree amplitudes in two possibly distinct field theories and multiply them in a certain way to generate the tree amplitudes of another theory, a third theory. And a famous and most famous example of this is the Yang-Mills theory. Times Yang-Mills theory gives the amplitudes of gravitons. And this precise map in 4 dimensions of the states is that the positive gluons, if you take two positive velocity gluons on the left and right copy of this double copy, you generate a graviton of positive velocity. Likewise, the matching up of two negative velocity gluons gives a negative velocity graviton. But you could also mix up negative and positive velocity. And under this double copy map, the velocities basically add. So you end up with scalars, two scalars, that in 4 dimensions are, and this is specifically in 4 dimensions, are the dilaton, identifiable as dilaton and axions. So that's why I call it gravity plus, because there's these extra scalars that will play a role in the double copy. There are many applications of the double copy. So just to put a bit into context, some versions of a field theory double copy has been utilized heavily to explore the UV structure of supergravity theories and explore finiteness. There are, of course, recent applications in the context of binary in spirals and gravitational radiation, where a double copy is used in the context of generating amplitudes that allow you to calculate to third post-Minkowskian order the effective potential for these binary in spirals. There are classical versions of the double copy. Since this works at tree level for all 3 amplitudes, it should also work at the level of equations of motion, because that is essentially both captures the classical physics in different ways. And so there's a whole industry now of studying the double copy at the level of equations of motion. There are many other cases that I've listed just in keywords here where the double copy has been used. So how does the double copy work? So let me try to sort of, from a basic 4-point aspect, indicate what is so special about the double copy. So gluon amplitudes in Yang-Mills theory can be color ordered. That means that we can factor out a trace. And what we have left is the partial amplitude with a particular ordering that pertains, cyclic ordering that pertains to this trace. And again, this is just 3 amplitudes. So if I look at the partial amplitude with color ordering 1, 2, 3, 4, it necessarily will have an S channel exchange and a U channel exchange. U is what I call 1, 4. But since 1 and 3 are not adjacent, there can be no T channel exchange. If I interchange 4 and 3, there's an S and T channel exchange, but not a U channel exchange. And though this comes down to saying where these partial amplitudes can have simple poles. On the other hand, graviton amplitudes obviously have no color structure. So the 4-point graviton amplitude has S, T, and U channels. So how can we possibly take take some kind of product of two partial gluon amplitudes and get a graviton amplitude without risk of doubling the poles, like I would if I multiply these two partial amplitudes together, I would double the S pole, and then at the same time also generate all the correct poles? The answer to this is that the double copy has a kernel. And in the particular case of just simply multiplying the first and second amplitude I've listed here together, that double copy kernel is simply minus the Mandelstam variable S. What this S takes care of is canceling the potential double pole in S that you would get out of multiplying the two partial amplitudes. And the product will then automatically have a simple pole in S, T, and U. So at least you can see how this has the right simple pole structure. But what is remarkable is that on this pole structure, you get a factorization of the amplitudes into the correct 3-point graviton amplitudes. And that is very non-trivial. I could, of course, also have taken the product of the first amplitude with itself, just to see what I would get. But then you see that I would double both the S and the U poles. And so I compensate by having a kernel that has both S and U. And then I have to add by hand the T-channel pole, and I can just do this way. It looks like a miracle that this should actually produce the correct graviton amplitudes. And from the point of Feynman rules, it looks entirely impossible. Nonetheless, this is true. And both these relations that I wrote here correctly calculate full graviton amplitudes. And they're examples of what are known as field theory KLT relations that would arrive first by Cavall, Llewellyn, and Tai in the mid-80s in context of string theory. And this is the field theory limit of that result. But now I gave you two different relations that I told you calculate for graviton amplitudes. If this has to be true, then the difference of these two expressions must be 0. And that requires the Yang-Mills amplitudes to satisfy a linear relationship, which is this one here. Now, this is a relationship that does happen to be true for Yang-Mills amplitudes. And it's an example of a so-called BCJ or Baron-Carrasco-Johansson relation at 4 point. In general, in order to have a sort of basis independence, in order to have a correct graviton amplitude, no matter which color structures I would choose for the input amplitudes in Yang-Mills, my Yang-Mills amplitudes have to satisfy a set of relations that they happen to do, which are the Gleichkopf relations, KK relations, which at 4 point amounts to trace reversal and U1 decoupling, as well as this BCJ relation that I listed an example of here. So if I go to endpoint, there are similar forms of the double copy. There's now a sum over products of amplitudes on the left Yang-Mills factor and the right Yang-Mills factor. And then there's a kernel which generalizes the form we had before. It's now some structure that depends on the endpoint Mandelstam variables. And there's a sum over color structures, of which that turns out to be n-3 factorial at endpoints. So these are double sum over n-3 factorial different color structures that you multiply together. And which ones you pick to sum over is the result of that is independent of that choice, and that is guaranteed by the KK and BCJ relations. So flipping this around, I can ask what theories can give a sensible double copy, and this gives me a selection criterion on the space of field theories, namely that theories that have some kind of color structure are double copyable so long as the theory's tree amplitudes obey the KK and BCJ relations. And these KK and BCJ relations exactly reduce the number of color orderings from n-1 factorial, which just takes care of the cyclic trace, to n-3 factorial, which is the correct number to sum over here. So it sort of gives the right rank choice, if you wish. So in a sense, this gives a new way to explore the space of field theories, namely by asking which theories can be possible input and output of the double copy. And not all theories, not all cases will satisfy KK and BCJ relations. And let me give you some examples of which ones do. We already mentioned that Yang-Mills theory satisfies this criteria. I can supersymmetrize Yang-Mills n equals 1, n equals 2, n equals 4, and those amplitudes will also satisfy KK and BCJ. Chiral perturbation theory, in the sense of the nonlinear sigma model UN times UN mod UN, which is the low energy theory of pions, satisfies this criterion too, and it double copies to something called Galileans. There's also a model that I'll talk a little bit more about later, which is called the bi-adjoint scalar model that satisfies this criterion. We'll come back to what that is. It plays a central role in what I'll talk about. You might also ask, what about higher derivative operators in effective field theories? Now, characterizing and finding a basis of higher derivative operators is an important subject, for example, for standard model effective field theories, and amplitudes methods there are gaining more traction, as you have probably seen in many different contexts. And so the statement I want to offer here is that amplitudes offer a very efficient, systematic way to characterize the high derivative operators and pick a basis for them. So what is known? Well, we know that leading order standard Yang-Mills, as I said, that satisfies KK-BCJ. And it's known from the past, in particular in a paper by Bertel and Dixon, that F cubed also does this. It has the same color structure as standard Yang-Mills and satisfies the same criteria. Bertel and Dixon also noticed that F to the 4 does not satisfy this criteria. There's one such operator, and here I'm focusing on the simply MHV plus plus minus minus sector at 4 point, but F to the 4 does not satisfy KK-BCJ relations, no matter which way you contract the indices. If you look at D squared F to the 4, there are 2 independent operators that contribute to MHV amplitudes, so 2 independent matrix elements. One satisfies KK-BCJ, the other one does not. And D to the 4, F to the 4, 1 out of 3 does. So there's clearly some selection criteria that is happening. If I were to do the same in Chi-PT, there's a similar pattern that you can see. The leading order 2 derivative theories obey these relations. There are 2 operators at 4 derivative order. Neither of them satisfy these criteria, but one does at D to the 6, phi to the 4, and so on. There's some particular set of operators that do. So it'd be nice to get some understanding of why are some operators allowed while other ones are not. Does it have to do with the particular color structures? Are there other things that make them special, so to speak? And then what we're really after here is what I described here. Is this the most general story in the context of the double copy? So let's take a step back and see what it is that we're actually doing. So we have some KLT type double copy formula. We take Yang-Mills as the left sector and add higher derivatives, and the same in the right sector. And then we generate gravity, axion dilaton gravity, with high derivative corrections too. But basically, this is like Taylor expanding and the low energy expansion, the left and the right amplitudes and the result. But shouldn't you also then do higher derivative corrections, in other words, momentum corrections to the double copy kernel? That would seem like a sensible thing to do. Now, you might say, does such a thing even exist? And so we can look back to string theory and say that certainly one example of such high derivative corrections exists in the kernel. After all, KLT came from string theory, where the formula will say that the closed string tree amplitude is a product of open string tree amplitudes with some particular kernel, which is not the same as the one in field theory, but which reduces to the field theory one I described in the limit where the string alpha prime that controls the tension of the strings goes to 0. So for example, if I look at a particular element of the kernel, it is actually amounts to just being a sign of the Mandelstam variable S. And when I expand this in the low energy expansion in small alpha prime compared to the energy scale, I see that the leading order term is exactly the S factor I argued that we had to cancel double poles in these in this double copy of the 1, 2, 3, 4 with the 1, 2, 4, 3 sector. But then there are certain high derivative corrections that occur. It's also clear that these high derivative corrections that occur are not the most generic one you might have thought of writing down. For example, because this is an expansion of sign of S, essentially, there's no U or T dependence on this. Why does it only depend on S? This seems very special. Also, because it's an expansion of sign, there are only odd powers in S. But if I had just made a guess of what the next order would be, I would have set some parameter times S squared plus some other parameter times T squared. Why shouldn't I be allowed to have that? So strings provide a very particular higher derivative kernel, but it's not entirely clear that it's the only one you can have. On the other hand, I argued before that when I write down the kernel, I had to sort of have a kernel that probably took into account that the pole structure was generating something on the left-hand side that could arise as tree amplitudes in a local theory. So it couldn't have double poles. It had to have poles in the right places. And it's clear that once I start messing around with the kernel, I could wreck that structure very easily. And you can easily write down an example that sort of one of the naivest thing you do to modify this kernel will produce spurious poles on the left-hand side. So the key question here is then, what are the rules for generalizing the KLT kernel in such a way that you preserve the properties that these are amplitudes that arise in local theories? So what we're presenting in the forthcoming work is a proposal for generalizing the double copy. And what we'll do this is formulating a set of bootstrap equations for the kernel. And we can solve these equations systematically to find the most generic higher derivative corrections to the kernel. That we can use then to explore what makes the string theory kernel special. And we can explore whether there are other versions of the double copy, not just higher derivative expansions of the known ones, but new versions, maybe that starts at a different point, that are solutions to these bootstrap double copy equations. And this is work that will come out hopefully very soon with postdoc at Michigan, Huanheng Chi, my student Aiden Hedderske, former student Calma Jones, who's now at UCLA as a postdoc, and Sruti Paranchapi, who just graduated and will be going to UC Davis. Now, the proposal for doing this, it relies on a principle, and it's good to have principles. So I will tell you what that is. It's relying on the idea of something called a KLT algebra, which I'll now introduce. So going back to the field theory double copy, I told you that Yang-Mills theory times Yang-Mills theories give gravity axion dilaton gravity. And you can use these other copies that I mentioned, n equals 4 super Yang-Mills, for example, chi-pt, and look at this map as a multiplication table. You can summarize what the multiplication is of the left sector with the right sector and what you get out. One of the things that appears in this context is that I have the byte adjoint scalar model, which I'll tell you a little bit more about what it is, but it has a very special property. It has the property that whatever you multiply it by in the double copy construction gives you out the same answer. And I want to emphasize that you use the same kernel for all these, you basically decide on you have your KLT kernel given, and then you use the same kernel for all these different double products. But for these double products, this biadjoint scalar model acts as the identity element. And so we can summarize this by saying that this has exactly the properties that an identity element should have. Moreover, the string theory KLT kernel changes what the multiplication rule is, and therefore it also changes what the identity element is, but otherwise it satisfies exactly the same kind of algebra. And so we take that as our leading principle, namely that this KLT algebra with these three identities here is the fundamental principle for generalizing the double copy. And we'll see that this leads to some very interesting results. In particular, you can see that if I change the KLT kernel, the multiplication rule, I must also change what the rule for the identity element is. And so this creates a clean link between the identity element of the KLT algebra and the product rule, which is defined by the KLT kernel. And so if you want to modify the kernel, you have to modify the identity element. And these two things, as I'll show you next, turn out to be intimately linked to each other. Moreover, these two other algebraic equations that basically are defining equations for what an identity element are in product with other things will generalize the KK-BCJ relations that I showed you before for field theory, but they will generalize them in a way that for the string theory case are known as monodromy relations, but in this context, we will call them generalized KK-BCJ relations. So that's the setup for this exploration. So in what sense is this now a bootstrap equation? Well, first, let me tell you what this biadjoint scalar model actually is. So it's a very simple theory. It has a scalar field, which has adjoint, it transforms in the adjoint of two different color groups. So let's call that color group UN times UN prime. And this field is as adjoint indices for both of these two color factors. So it has a kinetic term, which is invariant under those color structures. And then it has a simple cubic interaction where the fields are contracting with a fully antisymmetric structure constants. Very, very simple theory that in ways shows up quite naturally in the context of the double copy, in particular in the BCJ form that was found by Bernd Carrasco and Johansson some years ago. So what is the statement that biadjoint scalar theory multiplies with itself to give itself? Well, we could write it out in terms of the usual double sum over n minus 3 factorial color orderings with our KLT kernel as we know it in field theory. And then it simply says that when you sum over color orderings that match up in a matrix multiplication way, you generate certain color orderings of the same amplitudes in the same theory. You see, this actually is exactly matrix multiplication. So I could write it in terms of submatrices that are n minus 3 factorial times n minus 3 factorial. And that's exactly also the dimensions of the kernel, because that's what it sits in here. That's what the sum was originally to begin with. So you see, given this relation that has to be satisfied, which encompasses what 1 equals 1 times 1 means, I could multiply now on the inverse of the Mn submatrices on the left and the right, which turns out that these indices do exactly exist. And I find that the clean link between the identity element and the KLT kernel is simply that the KLT kernel is just the inverse of the submatrix of amplitudes in the biadjoint scalar model. This was an observation that was first made, in fact, by Cacciaso in the context of scattering equations. So the lesson here is that the KLTL kernel is this inverse of biadjoint scalar amplitudes. And moreover, it was noticed by Mesera a few years ago that the string KLT kernel is also the inverse of a similar rank submatrix of amplitude, but in a different model, which essentially is a biadjoint on the alpha prime expansion. It's the biadjoint scalar model plus certain selective high energy corrections or high derivative corrections controlled by alpha prime, but with no parameter freedom. So what should we do to generalize the double copy as a derivative expansion? Well, it sounds like the right approach is to take the biadjoint scalar model and add to it all possible higher derivative correction with arbitrary Wilson parameters that are then subject to this identity constraint, this bootstrap equation, that then will determine solutions for the coefficients A, I, J. In what sense is this restrictive? It's restrictive in the sense that we want to ensure that once I remove any higher derivative corrections and get back to my biadjoint theory, then the rank of my matrix should not change, because that would render the inverse here singular in the low energy limit, and we can't have that. That would be inconsistent. So the rank condition basically comes down to the fact that as you add higher derivative corrections, the amplitudes that are generated in the biadjoint scalar must only have n-3 factorial independent ones, so to speak. So anyway, this gives a bootstrap that links and then allows you to restrict the amplitudes and give you as the inverse the KLT kernel that you desire. When you do that, this is what you find at 4 point. And of course, there's also higher point, but I'll come to that shortly. So at 4 point, we have our usual cubic biadjoint scalar model here in the first line. And it turns out that the bootstrap equations allow us to have 3 different types of interactions at the level of 2 derivatives and 4 phi fields. So let me make some comments about this. First of all, we notice that there's a color structure here, which is no longer just the antisymmetric structure constants, but also these more familiar anomaly type color structures, which are the fully symmetric DABCs. Now, one thing that is not allowed is to have a cubic term, which involves the Ds. This simply does not solve the 4-point rank 1 bootstrap equations. There's also no phi to the 4 term. You notice here that I added it, but this is not compatible either with the bootstrap equation. It sets that coefficient A00 to 0. Now, there are D terms that appear here in the 2 derivative terms, and that the result of having those is that the U1 decoupling identities that we were familiar from the standard KK relations are modified. They no longer hold, but this is familiar even from the strings case, where the monodromy relations that generalize these relations also violate the U1 decoupling, or so modify the U1 decoupling identities. Notice that while there are 3 distinct interactions here, they're controlled by only 2 parameters that we've called A left and A right. And the strings kernel has the property that A left equals A right equals, in some units, minus 1/6. So those are completely fixed. There's absolutely no freedom. But the generalized kernel has the freedom of treating the left and the right sector. You can sort of see that this is the left and the right sector that are treated differently in the terms of the U1 violation. And that gives this new form of the double copy a certain sort of heterotic sense or type, because it treats the left and the right sectors differently. We also have results at higher orders in the derivative expansion, but I just wanted to focus here on the clear differences that appear already in the leading order corrections that you have. Moreover, notice that you can't have the identity that does not violate, sort of the derivative correction that does not violate the U1 identities of this order, namely the one with the 4 Fs. You can't have those without violating U1. You must violate U1 of this order. You could place restrictions that don't violate U1, but in any case, this is the setup. So what do we get out then of calculating the amplitudes from here and inverting the kernel and getting generalized KK BCJ relations from it? Well, let's apply it to Yang-Mills plus higher derivatives. The leading order term that I've written here is the usual Yang-Mills factor. Then there's a term here that arises from a pole term with 2 insertions of trace F³ vertices. All those are standard and appear in the normal double copy too. But the new feature here is that now you're allowed to use F⁴ in the double copy. And its coefficient is exactly controlled by the left sector coefficient that sits right here in the leading order correction to the kernel. So that allows you now to double copy a wider range of theories. There's an unchanged coefficient here that comes from d squared F⁴, and then of course higher derivative terms as well, which we computed to quite high order, but it suffices here to just show a few terms. So if I compare now the higher orders indicated with the blue check mark here are the operators that now are allowed by the generalized KK BCJ relations and the generalized—
5 minutes, Henriette.
Got it, thank you. And whenever you set those higher derivative corrections in the kernel to 0, these contributions marked in blue go away. So what you see is that the generalized kernel continues to have restricted behavior, but it allows more operators to be double copied than before. We could do the same thing for chi-pt, which I just wanted to mention since this is pion physics. Still, 4 derivative interactions at 4' are not allowed, but now another operator gets to be allowed. And a fun little fact is that if you insist on the kernel being the same for these 2 different types of the double copy, Yang-Mills with Yang-Mills, chi-pt with chi-pt, or Yang-Mills with chi-pt, then you find that the coefficients of the input amplitudes with F⁴ and d⁶ phi⁴ are actually neatly linked to each other by being fully determined by the same A left or A right in the kernel. I don't know any other aspects where there's a link between these type of coefficients, which are even of different dimensionalities. Okay, so what do you get out of double copying Yang-Mills with high derivatives? Here I'm focusing on the MHV sector. First term, usual Einstein, and then there's an S-pole term, which is kind of interesting because this corresponds to a scalar exchange. And what we find is that when you keep the couplings on the left and the right arbitrary and not necessarily the same, you will have an exchange that contributes to this term from both the dilaton and the axion. So Dixon and Brodel in the past saw the dilaton exchange, but because they have identical couplings on the left and the right, they didn't see the axion exchange, but it's there, and we cleanly identified. At the level of R⁴, you get a coupling that is generated in part by the leading Yang-Mills and the d squared F⁴ terms. That is present also in the usual field theory lemma of the double copy, but now there's a shift of the coefficient which generalizes what this coefficient can be. That vanishes in string theory, but is allowed in the more general level of the kernel. This comes from d⁴ phi⁴ terms in the corrections to the biaxial scalar model. In all of the many cases we have checked at 4 the same operators are produced by the double copy, but with shifts in the coefficients just like this one due to the corrected kernel. I want to mention briefly at higher point, we need to go to higher point to make sure that, say, 5 Bootstrap doesn't restrict the 4 kernels, because that would put us in trouble. Then how high orders would we have to go to really fix things? And so we study this at 5 where we see the 24 different distinct color orderings. That means that it turns out we can parameterize all these different amplitudes 24 by 24 by just 8 functions. We solve the Bootstrap equations, and we find that there are no constraints placed on 4 coefficients whatsoever. And up to quadratic order and Mandelstam's, in fact, those 4 coefficients entirely fix everything. At the next order, you can start having a little bit of freedom from local operators. And then we can test this for this self-dual sector of 5 Yang-Mills plus higher derivatives and simply just test the procedure. But this is an important consistency check for the Bootstrap, and it passes that. So just to summarize, what we have is a way of generalizing the double copy that allows you to double copy more theories, effective field theories, in a systematic fashion. And these are the blue input theories that you can generalize, and they generalize into higher derivative theories surrounding in the neighborhoods of these standard field theories. It's just an overview map. And that key point is here that we have a generalization of the KLT kernel. I want to notice again, the field theory landscape is incredibly rich. And one of the things that is special about the double copy is that it links theories that are so widely different. It links with normalizable theories like Yang-Mills, with conformal field theories like N=4 super Yang-Mills, with non-renormalizable but amazing phenomenological EFTs like gravity and chiral perturbation theory. There are low energy effective field theories on deep brains involved in this. There are Galileans that are used in cosmology, but in self are in the swampland. And then there's this bi-adjoint theory that I described, who has a potential that's unbounded below and appears to not make sense as a quantum theory, but now with high derivative corrections also. So there's a very interesting question here that this clearly slices, the selection criteria slices the space of field theories in a way that we're not used to from any of the other ways that we tend to explore the space of field theories. So this work is a first systematic study of these generalizations of KLT double copy kernels. There's previous work by Carrasco with different color structures, but this is really sort of a really systematic bottom-up way of incorporating such corrections and exactly seeing what the allowed possibilities are. I want to finish by emphasizing that the double copy is truly amazing. The 4-point graviton amplitude has contributions from these 3 diagrams, each of which is basically a page in LaTeX format of what you get in a standard Dedondo gauge. And somehow they add up to magically give a product structure of 2 quite simple Yang-Mills amplitudes. This requires a really intricate and fascinating relationship between left and right sector amplitudes into the double copy in order to produce something that makes sense. So we feel this new freedom in the kernel deserves further investigations, moving higher derivative corrections around between kernel and amplitude by shifting Wilson coefficients. Is this a possibility? What are the interplay with positivity constraints from swampland conditions on UV compatibility? Is the relation with the EFT hedron? And we'd like to know what makes the string KLT kernel that we now generalized, what makes it so special? Is it in some sense a minimal kernel? And we'd like to know if there exist other branches of the double copy that don't start with bi-adjoint scalar, but entirely new solution. So I'll finish by acknowledging my wonderful collaborators, and especially also my home collaborators, who is an essential part of making everything work. So thank you.
Thank you, Henriette, for a wonderful talk. So let's see, we have a question. Could you please comment on the applicability to theories with multiple particles, possibly in the fundamental representation?
Yeah, so there has been work by Henrik Johansson on studying double copy criteria for amplitudes with fundamental matter also, such as QCD, so Yang-Mills with actual quark matter and so on. So that is one aspect I wanted to comment. So changing the group structure, like to not just have adjoint, but also fundamental representation has been looked at, not so much, I think, for the purpose of understanding what they double copy to, though there are some interesting aspects of that from positive geometry aspects, but more for the aspect of getting equivalence of BCJ relations. That means that for, say, phenomenological purposes, there are fewer amplitudes that you actually need to calculate because you get the rest for free doing such through such interrelationships. That's one aspect. The other aspect that is, of course, of interest is that everything I described here was with massless particles. There's been a study of what happens with massive particles. And one of the key papers about that was written by Callum Jones and Shruti Paranchapi with Laura Johnson recently. And they showed that there's a certain spectrum condition you must have starting at 5 point for the double copy to sensibly work. And one set of theories that would satisfy this are ones that come from dimensional reduction, obviously. But they have a set of spectrum conditions that you must have. And so that's that sort of work that is being explored now of what does the double copy mean with massive particles and what are the criteria for that to work. And that actually, their paper was quite influential for our generalizations here also.
Great. We have a minute for another question. A naive question. Well, double copy has many amazing features and help us explore the vast field theory space. Should we view the double copy as physical constraints for a consistent field theory, or does it help us understand some subspace of field theory?
So it's a great question. So it's clear that it is a selection principle that selects some subspace of field theories that satisfy the criteria of being allowed to be a double copyable thing, right? And not all theories allow this. So for example, if you took chiral perturbation theory, the Westermino-Witten term, the Westermino-Witten term doesn't apply. This doesn't satisfy these criteria. So it's sort of ruled out, but it's important, of course, in other contexts. So it is a selection criteria. It's not, as I emphasized, it is something that slices the theory space in a different way, in that it is certainly not something that necessarily cares about swampland. But these ideas that this amplitude, that the Wilson coefficient gets shifted around by these higher derivative corrections are very important, because swampland conditions typically place positivity and interrelationship constraints on these coefficients. And when you then start shifting them around, you might get into violations of those criteria. And those are important and interesting to combine with this analysis.
Great. There is another question. Maybe you can answer it online, but I think we need to go to our next talk.